Thanks everyone, especially Sahar for inviting me here. Jason Ren, I'm been with Princeton. Uh, I I have a title, as you see, is it's been a reflection for me, to be honest. In the past, I guess, few years, I traditionally has been a engineering person, right? We develop technologies for resource recovery, energy recovery, water, wastewater treatment, things like that, right? But in recent years, I really I've seen some of your work and also really to say, okay, what does this methane actually interact with wastewater? Even though I know it's we've done that on energy aspect of things, right? So that's why I give this talk. I know you guys are expert on this part, I would love to again interact more and collaborate as possible. So in terms of, again, greenhouse gas emissions, wastewater or in general waste sector has not been certainly a focal point. But ways we see is, again, grid decarbonizing, the transportation sector decarbonizing, the other sectors start to emerge to become more important, including the wastewater sector. Wastewater sector has a very interesting, I guess, profile in terms of emissions where it one of the largest ones for non-CO2 emissions, especially for N2 and methane. So today I focus on methane. There's certainly some N2 work we do as well. IPCC actually highlighted it in its latest report 3 years ago, really to try to think about this sector can be getting more important. For those of you who don't know, actually wastewater treatment plant is just basically happens when you flush the toilet, when you after you shower, right? All the water actually went to a underground sewer system. If you would remind you of the sort of big horror movies in the New York City sewer system, like whether it's Godzilla or Pets 2, whatever things, movies you remember, right? So what happens is this water would be then collected and pumped up and to be treated in generally large, we talk about the city scale, large facility like this one. So this is a Denver Metro. Treats about 130 million gallon per day, serving more than 2 million people around Denver metro area. So all you see is the circles and squares, right? There's several important, what we call unit operations important in this case, where you can see those sort of square tanks that we call aeration tanks. Those are the major units for biological reactions for removing dissolved organic matters. And then we actually collect the sludge at the bottom, whether it's organic particle or the bacterial cells. Then we separate them actually through physical process called a clarifier. You have the water, clean water, then discharge to the nearby river as you can there after disinfection. I'm simplifying it. It's many different steps. But also we collect the sludge at the bottom that we would have sent them to this sort of a sealed digesters. Many of you are familiar with this sort of the sealed anaerobic digestion. Before that, we have to have dewatering process. After that, we have the disposal of the biosolid process, right? So that's where you will see from my talk, mostly the methanogenesis happens. These are all biogenic methane. Why I got interested in this field, I guess, a few years back, was really actually somehow inspired by what a lot of you guys doing. Like it's been Princeton is known for actually some of the folks you probably know, Max Celia and other folks doing really understand the natural gas leaking right through oil, especially and abandoned oil gas wells, and really sort of thinking, okay, what are the big of issue? How do we monitor? How do we mitigate? Right? And on the other side, we talk about decarbonization process where if there is a goal still by mid-century, we could really achieve some sort of net zero or close to it. Probably your next car needs to change to a clean fuel vehicle, right? For industrial is even longer time frame. But for wastewater, it's this technologies last for century, right? So it's really if you make any wrong decision, in terms of implementing a new technology, we're talking about at least tens of millions of dollars investment. If you would have put in a technology, you missed the boat already. So that's what I start to think rather than, well, in addition to the technology development, I still develop technologies for the industry. But what are the sort of implications or consequences if we really don't look into the greenhouse gas emission aspect rather than we only focusing, oh, we save this much energy and or cost and things like that, right? So that's really prompt me to think much more holistically in terms of the emission aspect of it. So then with that, really what we're trying to think about is, okay, you have to understand the benchmark, right? So this is where the study we did really trying to understand, okay, what do we know about it? Where basically different from, again, transportation sector, energy sector, rarely is a emission is, I don't want to say easily defined, but fairly straightforwardly defined. The wastewater sector is quite complicated. It does have the direct emission, as you see here, N2O methane through actually the treatment process. Nothing we can avoid, to be honest, but we can try to reduce them, but also through, again, the fuel use and other things, right? But also, for most treatment plants, they are among the largest energy consumer of any town, any city. Again, you have to move, again, hundreds of millions of gallons of water every day. Think about how much energy you would use. You have heat up the reactor sometimes, right? So that's, again, a lot of energy use. And think about the concrete tanks we use. Think about the chemical we have to dose into those amount of water. There's a lot of chemical and material use, so that's the scope 3. So the sector certainly has a very complex nature in terms of how to quantify the emissions, right? So today I mainly focus on the scope 1, only on methane, but also with the implication and interaction with the energy aspect, because it is, after all, is energy source as well. We started a bit really to collaborating with Professor Donald's group. Some of you may know him. He's really expert on using a mobile lab with sensors on electric car to drive around to looking into the emission profile of different greenhouse gases, right? Starting from oil, gas, and ammonia plants and other things. So we really collaborated did many actually drives around the country and to look into, okay, what the emission looks like. So these are, I have to highlight, these are plant level emissions, not the individual unit level. I'll talk about that in a minute. And the finding was really very, I would say, interesting, or on the other side, alarming. So the finding from the groundwork was that the actual emissions through the monitoring, these are real emissions, was about twice greater than the emission factor assigned to this sector by IPCC or EPA. So that's basically give you a sense, okay, this is actually something that we need to get the bottom of it. Since then, there'll be more actually studies, nearly 100 treatment plants. The car has drove by Mark's group, and we really helped them to understand the mechanisms and the nature of this industry. You can see certainly there's one thing take home was that the variation is huge. This plant's emission profile is very different than the other. And also you can see the actual emission measured in this, at least in using this method, is for the methane. Again, you can say the EPA estimated emission factor for methane is 270, and yet the number the studies got after 96 visits was more than double of that, right? So that's really give the sense, okay, there's a discrepancy, there's something we need to do to really understand what's going on, and certainly maybe IPCC can look into this to adjust some of the practice as well, certainly as a plant as well. So there's no way we can visit every plant, just like you guys, there's no way you can visit every abandoned wells. We actually have to use machine learning and many modeling process and literature mining and language models, whatever tools available for us to really get a broader understanding of the sector level emission, right? So that's why we really dig into anything we know from the literature, from published papers, from technical reports, from actually our interaction, from our own data and the interactions with the utilities and consulting partners. So build up the model to dissect into different units among the treatment process. Then we put that into again a database where we call a CWNS, a Clean Water Needs Survey. This was generally done by EPA every 5 years ish, but the most recent one was 2022. Before was there was a gap due to a variety of reasons was 2012. So the earlier study we did use the 2012 data, and recent study we used 2022 data. But basically, we were able to compile the emission profile from different type of plants, different type of technologies used, where they locate, what the emission profile looks like, fit into the 17,500 treatment plants actually known by EPA and documented on their operational or their construction level, that then we sort of fit that into the model. And then we would be able to sort of estimate what emission looks like, right? So sorry about the acronyms. Some of you may not familiar, but basically the axis is basically the different technologies. There are many different type of technologies people use to treat wastewater. There's a sequential batch reactor, there's traditional active sludge, there's a anoxic aerobic process, right? A different technology but achieve the same goal, try to clean up the water, right? And you can see what's interesting is certainly they sort of behave a little bit differently in terms of how much emission of methane they have. These are again based on literature data, not necessarily our own measurements, but we would generally trust actually these are a real measurement data, not modeling data. But one thing sort of stand out is really you can see from the first part, from the graph on the left is really this plant. This is a plant level that with anaerobic digestion units for sludge management, your emission is about actually 10 times higher than for the plant without sludge management, or at least anaerobic digestion. So you actually see certainly AD has been a major, I would say, focal point in terms of the methane leaking, right? There are some small leakage from, or I don't want to say leakage, some emissions from the other previous water units. For example, I'll talk to you just at the last part of this talk about the sewer methane. There's a bacteria, there's a archaea can produce methane if your sewer system become anaerobic. There's a methane dissolved. It's a fairly highly dissolved species, right? And then when you aerate the gas, when you aerate the process for biological treatment, then the methane can sort of get stripped out. So that sort of give you the sense like where methane can, wherever it's getting anaerobic, it's a help methane production, right? So that sort of gives you the sense, okay, we know where to focus on. Interestingly, without, I would say, any cooperation or collaboration in that case, our model actually showed fairly consistent actually findings with a ground level measurement that is about twice of IPCC estimates. That sort of again raise some sort of questions. Should we actually do more about it from both scientific engineering perspective, and also should we adjust emission factor and make it more reflective? So then I sort of just mentioned like the AD process itself, or I guess the train for sludge management itself within treatment plant count for more than 80% of the emission. So we sort of then narrow down to say, okay, what's happening with AD and what we can do about it, and what's the broader implication of the AD systems in wastewater. That's again connecting with the leaking itself with actually the general decarbonization goal, because why treatment plant have ADs? For one thing, it is a very effective process for managing the sludge reducing the volume, stabilize it, and because there's nutrients in there, nitrogen, phosphorus, and the potassium, other things, organics. So people have used this as an effluent, what we call biosolids for land application for actually fertilizers, right? And certainly the methane, which is about 60% in the biogas, or what some of you call flue gas, is actually a renewable energy source. People use it for combined heat and power, for electricity production, heat, and or they upgrade them into renewable natural gas, RNG. I'll mention that just a few minutes. So I won't get into the detail of the technological process, but really what we put into this big domes are the sludge, which contains organic matters, mostly recalcitrant ones, hard to break down. And what's coming out of this would include CO2, methane, and organic materials we call biosolid. So why this process is very important is when you look into the broader picture as a traditional wastewater guy, we did not pay attention to much leakage, just to be honest. We say, okay, how do we maximize recover of the biogas or methane containing biogas so we can recover renewable energy, right? So this is a bioenergy, just like agricultural biogas, right? And that would offset the energy needs of the treatment plants, and that would certainly not only saving the bills, but also to reducing the carbon emissions if the grid is electricity is relatively dirty, right? So as you can see, it does play multiple roles. This systems. So I guess about 2 years ago, I started to think of me a little bit more broader because my expertise has been again a lot of about the energy water nexus. How do we make the treatment plant more energy neutral, right? How do we recover more renewable energy, right? Right, whether it's a biogas or hydrogen or other things, right? So then I start to think like really, okay, what's the interactions between this biogas recovery out of AD systems versus the general decarbonization trend, like where the grid getting cleaner, right? So we did this study. So there's interaction between the scope 1 emission where the leakage of the well, not that we haven't talked about leakage yet, where basically you would use a AD biogas as energy source versus the grid electricity, right? With the decarbonization of the grid, especially Northeast, Northwest, and Texas somewhere, where it actually the grid is getting cleaner and cleaner and cleaner, that means it's recovering actually the biogas for renewable energy production has a less and less impact in terms of the climate benefits. I can tell you some places like Toronto or some other places really to rethink whether AD is necessary for them because recovering that part of renewable energy is actually more costly and more I guess lending to actually more burdensome than simply buying the clean electricity. However, when you look at the potential for certain places, for example, East Bay Mud in San Francisco, they were able to fully take advantage of biogas and energy production to be carbon neutral. They don't really need actually much grid electricity anymore, despite the fact that actually their grid is pretty clean, right? So it's really what the plant wants, right? In many cases. So the graph on the right, you can see if you would be fully taking advantage of the AD potential in terms of biogas converting to combined heat and power, for some states, it's actually even possible to make it actually carbon negative, meaning actually it's the energy itself would compensate actually all the other emissions and it certainly will save the emissions. So that's certainly still a very important, promising sort of pathway to expand the AD operations to recover energy and certainly the fertilizer and other benefits in terms of sludge management, right? However, I would have to credit to our consulting partners and collaborators that they've done a lot of groundwork in addition to our mobile lab. But you can see from this is by Chuang Le and John Willis at Brown Cowell. So they sort of done the groundwork to see there are leakages. So these are digester like covers, right? And you do see from the OGI camera, you see the leaking over there, and some even on the wall. And this was photo, actually, the video taken by John Willis. You can see the bubble actually sort of coming up periodically. Those are again containing 60% of methane, and it's an open field. So that's really a prompt into the question is how much of the leakage can become an issue. There would be leaking anyway, like oil and gas wells anyway, right? But the issue would be it touch into multiple fronts, right? I just talk about the climate front. If that you have methane leakage, that would basically have again scope 1 emission, which is not good. But it's also for many of the utilities, it's also super important to say, okay, if we would prevent leakage, you can save a lot of money. You can recover more bioenergy, right? And also there's a safety issue related to that because it's inflammable, right? There's a lot of multiple benefits if you would and really quantify where this come from and how do we reduce it. So how much leakage are there? So again, there's really very limited data. That's why I would call many of you are experts on this. This is certainly a very new area to many of you. There's not much measurements done, but we took advantage of our own skill in terms of literature mining and modeling. You can see for systems with CHP, in average, you have about 7.5, 7.4% leakage. And if you actually have about RNG, that's even higher. So that sort of give you the idea, oh wow, about 10% leakage in there. That we lost, it's a lost opportunity, right? From the operation perspective, and certainly a increased risk in terms of the direct emission on that, right? So that's why it's really getting very interesting to say, okay, then I really start to think, can we really do a analysis like where is the I would say the deal breaker or the tipping point is. So this is a paper just actually accepted by Nature Sustainability, really looking at the interaction we call threshold, that where basically if we would mapping out how much leakage are there, which would generate scope 1 emission, right, by methane. Their CO2, well, the CO2 is biogenic, right? We consider it carbon neutral. And then on the other side, there's two main actually valorization pathways. Either you do combined heat and power, or you do renewable natural gas, right? So you upgrade that. And through that process, it's actually fairly different pathways. And then we sort of, again, look into different scenarios and put into, again, the energy aspect of it. If the energy recovered by through this process, whether CHP or RNG, different format, would be offset which I mean is the scope 2 emission saved by using renewable energy to replace the grid energy, right? You have scope 2 emission savings. How much of the leakage would totally offset that? If 5% of it's 83%, 80% times worse than CO2, right, in short term, then it's whether it's actually the environmental benefit is offset, or sometimes if a higher leakage, it even would reverse the environmental benefit or climate benefit, right? So that's basically we put it into different scenarios. You can see for CHP, the threshold is, I would say, again, depending on the full heat recovery or only AD recovery, the threshold is say about 8% to say, again 6%-ish. And there's a future actually threshold. The future threshold is lower than the current threshold because of the benefit of the bioenergy in terms of climate emission saving is getting smaller, right? Because the grid is getting cleaner, if I make myself clear on this part, right? So basically, if you're doing great in terms of your electricity, it's actually clean. There's no more point to actually producing the biogas anymore for climate benefits. The cost is a different story, right? That's something I think Sahara is working on. Anyway, so then RNG, you can see the threshold is even more stringent. It's about 5%, which means if you have like 5 to 10% of leaking from the biogas plant or the system, unfortunately, actually, the bioenergy benefit in terms of saved emission from the grid is totally offset. And then it certainly depends on where you live. So we basically put into the e-grid mapping, certainly it's relatively rough. You can see from the actually the states have much cleaner electricity grid. Certainly, the threshold is lower, meaning that you really need to prevent leakage in order to keep the climate benefits or emission benefits. For the grid that needs more decarbonization, like Midwest, that certainly the threshold is higher. Doesn't mean you don't want to control the leaking, but this is again really analytical to give the perspectives what it means in terms of leaking, right? So then, when you think about this overall, how does that really have implications on policy side? In fact, the editor asked us to write a policy brief in company with a research paper. Really, when you look at this, whether you use the emission factor, that's one number from IPCC. This was done by consulting GWI. Methane counts for about 25% of the emission or it put it actually the wastewater into the broader spectrum. This is not necessarily the latest one. Say wastewater counts for 7%. What happens if you actually count to the actual observation I showed you, whether it's from the mobile lab, from the literature, other people have done the measurements, or from the models we've done. Uh, the wastewater, the piece from wastewater are probably going to increase, right, from this pie. And that was actually called attention by EPA just as of last year when EPA still was working on the latest inventory. They sort of cited multiple studies from our group and other groups to really say, okay, there may be a time to revisit this process. So I would still hope this would happen sooner or later, just to get the bottom of the science, right? That's very important to me as a scientist. One last thing I have to say, we really don't know much at all, but I feel can be another surprise to us is the methane emission from the sewer system or the wastewater pipeline under our foot. So there's a different type of the sewer pipes. Mostly we call it gravity sewer, so there's no energy. So basically water flow downward by gravity to the plant and they pump up, right? And sometimes they also, because of the geography, so they have the rising main source, so they have to pumping up. So either way, there's especially for rising main. So this system can get to what we call anaerobic, meaning there's not much enough oxygen in there, yet it's very organic, nutrient rich in the system. That the methanogenesis would happen. So you would have a very concentrated methane produced from the sewer system. But there's really not much measurement on this yet. There are several, for example, John Willis was one of the first ones at Brown Coldwell doing this. And there's some studies in Australia and Europe, but and North America, there's not much being done in there. So I'll show you one video I found on YouTube. This is basically happens that amount of methane in the sewer that what's going on in there. Okay. I'm not sure you can see the sound, but there's basically background music, nothing, people screaming. But you see that there's concentrated methane in the sewer that can cause not only climate issues, but big safety issues in there, right? There's again very limited data on the sewer emission. I hope there's more. If you guys interested, I would just really hope you guys can brainstorm how to do that part. There were studies basically again where you're located. For example, tropical fields. There's a studies on Thailand. There's one study basically say there's a tons of emissions from their sewer system. Partially because they have the decentralized sewers, they have septic tanks, and it's highly organically loading, and or they are very hot, right? There's not much actually methane in the actually dissolved. They actually emit out, right? So much higher. There's other studies. There's one in Paris basically saying the sewer methane accounts about 30% of the total methane wastewater sector emission, right? But again, we really don't know much about it. So because I don't have much data to do, but we know how to do models and we know the mechanisms. What we did, we use a proxy. This is again, people would may say, well, it's not real data, but really from the again for the sake of understanding, right? We don't know how much sewer globally methane produced, but we do know there's a tons of data actually on the bacteria or archaea microbial community in the sewer system. And we know very clearly there's a specific pathways how this methane are produced through we generally call three steps through first one called hydrolysis. Basically, these fermenters break down the polymers into monomers like glucose and the acidogenesis, where basically they produce bacteria will break down the sugar into different alcohols and different acids, and then the acidogens convert acids into methane into acetate. Then there's a different type of methanogen. There's a hydrogen trophic would use hydrogen CO2. There's acid elastic to use acetate. So we know all the biology happening in there, but by actually understanding what are the pathways that we would be able to predict or actually at least to understand, okay, what are the biological pathways that leads to the biological methane production in different sewer actually systems. And so again, this is a very biology and a data science driven on this part. We don't know the actual emission, but we can predict how much that looks like, right? And also we can say, okay, CO2 derived methane, biogenic methane versus acetate derived methane production versus methanol derived methane production, which actually leads to higher methane emission as compared to the other pathways, depending on what kind of methanogens in the sewer, right? So with that, we would try to correlate, okay, how do we, either way we can understand, we don't even try to control yet, but really trying to see the connections between the biology and the actual emission. So again, I don't know much in the sewer yet. Nobody knows much, but I do feel it's actually interesting because there's a sewer in a very special case is the methane can produce again from the sediment. There's could be methanogen in there. From the biofilm, actually within the water, this part is actually what's methane produced, and so that's when they get mostly anaerobic, right? So there's a lot of research questions like I would be interested to. Okay, so that's about it. I'm doing this really with a lot of collaboration through Water Research Foundation funded projects with Brown Coldwell, with Jacobs, with actually Sahar in Berkeley National Lab, with a lot of consulting and many utilities actually in partnership with us to truly try to understand the sector level emissions. Certainly methane is a big thing, and also N2O and other things. Do want to thank my group member for their great work, and thank you for your time here.